Yes, it has started. It has started. Let me now share the screen. I hope I am. Good. All right. So I allow this later. Okay. See, what we will do today is that, so we have built a number of circuits. So you can view any logic circuit. Am I audible? Just anybody just confirm I'm audible or not.
Yes, sir.
Yes, sir.
Thank you. Okay. So you have a logic circuit, and let's say it has a number of input. Let's say call it x1, x2, x3, and it has an output which is, let's say, called y. Right. So inside this box, there are gates and various types of basic gates, and they are connected in some way, in a cascade manner or some way. But if we look at the box, you can sort of express this output y as some function of x1, the inputs, as some function of the inputs. Okay, so one more thing we studied in this class is that this x1, x2, x3 as well as y, they are binary valued. That means they can take value either 1 or 0. And what we now want to, and we have studied several kind of cunning. For example, f can be an adder, f can be an comparator, so f can be anything. But but in all the cases, f is some kind of a function from the input to the output. So our next goal in this module of the course is to study this function in more detail. What kind of functions can be implemented using only logic gates? Of course, they will be Boolean functions, but what are their nature? How do we deal with them? How do we manipulate these functions? And uh, what we have is that we will often see that these functions can be represented by what is known as Boolean expressions. Boolean expressions. So what is a Boolean expression? It's something like some variables and maybe their complement or something like that. And they are connected by some operators, and then put a dot, which is the and the or operators. So they are represented by these kind of Boolean expressions. So what we want to do next is that instead of just talking about that this is a Boolean expression and all that, we would like to do a theoretically sound mathematical representation of these functions. We would like to do a mathematical representation of these functions. And we want to study the properties that these functions satisfy in terms of the mathematical representation. And why are we doing this? Because from a design point of view, from a practical point of view, our thing is that given some logic you want to implement, we look at these expressions. So there are 3 steps. First is you write down logical expression. Then there is a step, something called a minimization of the logic expression or the Boolean expression. That means you convert the expression into an equivalent form, which is easier to implement, which requires less number of gates, which is smaller, which is less costly. So these manipulations which convert any given Boolean expression into a minimum form, in a minimal form, those transformations are very important to us from the implementation point of view. They are important to us. And in order to study what are valid transformations and what type of transformations would help us, we would need to study the mathematical basis of or some kind of mathematical representation of these functions. And that is what we are going to do today. So the goal of whatever mathematical foundation we study today is to help us in this minimization process or this transformation process. Okay, so with this, let me go back to my slides. Are the slides visible? Just anybody confirm the slides are visible?
Yes.
Yes.
Yes, thank you. All right, so we'll start from a little more fundamental objects like sets and relations, and finally we'll end up defining an object called an lattice, and we'll see that all these Boolean functions we talked about, they can be represented as lattices. So these lattices are a nice representation, nice mathematical representations of these Boolean logic functions that we so far has been dealing with. Some of these topics you have already studied in discrete structure, but nevertheless we are again repeating them because I mean after so many years I also keep forgetting the definition sometimes and confuse between them. So it is always better to repeat them once more. Some of you who I hope many of you already remember them. That's very good. If you remember them well, and if I make a mistake, you correct me. Okay. So let's start from the very basic. So we start with everything is the basis of everything is something called a set. So it's a collection of elements, and these are some examples. So the set of all natural numbers, all integers, or 0 to all the integers, or if you drop the 0, all the positive integers 1, 2, 3. These are all example of sets. You can have z plus and z. You can have all the integers from negative and positive. So these are all examples of set. There are 2 special sets, as you know, universal sets, which comprises of everything, and the empty set or the null set, which does not have any element. Okay, so there are some Russell paradox. So if we consider the set of all sets which do not belong to itself, so is that set a element of set? Okay, so there are many. So in fact, the very definition of set depends on some fundamental assumptions in mathematics. Axiom of choice and other, it depends on fundamental assumptions. Okay, but what we are more interested, assuming that there is a definition of a set, what we are interested is set operations. That means given 2 or more sets, I want to produce a third set. Say you are given 2 sets A and B. I want to produce a third set by some way operating on these 2 sets. So A and B are kind of operands, and in this case, the set union is an operator, and A union B, after applying that operator on these two sets, you get a third set, which is the interunion of these two sets. Okay, so this kind of operators on sets are what we are more interested in. And moment we have these operators, that means you have basic sets and then you have operators on them, we start having an algebra over the sets. So algebra is nothing but how do you manipulate objects? How do you manipulate objects? The way you manipulate objects is you apply operator on them, either unitary operator or binary operators. You start applying operator on them and create newer objects. Okay, so the rules which apply to these operators, the rules which apply to creation of these newer objects would follow some laws or axioms, and a system comprising of certain sets, certain operators, and certain axioms would be called an algebra. So in the set we have some basic operations which you know of, that is the union operation, which is obvious, the intersection operation. So these are the Venn diagrams representing the output of applying these operators. And then you have the complement or the bar operator. Okay, so this bar is also sometimes represented as a prime or a tilde before that. So it's the complement operator. So these three are the fundamental operators in the set algebra. Okay, so using these operators, you can define other derived operations. For example, using the intersection and the complement operation, you can define the set difference operation. This way, by combining several such operators and maybe several such input operands, you can create what are called expressions, which are basically more complicated outputs. So you can, for example, you can have an expression A union B intersection C, where taking three input sets A, B, and C, you create a more complex set by applying this operator. So this would be called an expression. Note one thing, that you have a notion of the value of an expression. That means if you evaluate this A union B intersection C, if you evaluate this, you get another set. So the input is a set, output is also a set. That's what is important in algebra. Okay, so now there are some laws or axioms. What axioms mean is that there are two, you can write down two expressions in terms of sets and their operators. You can write two expressions and say that these two expressions are the same. That means if you apply the output, if you apply the same input to the first expression, and if you apply to the second input, same input to the second expressions, the output sets that you get after evaluating the expressions would be same for both these expressions. Usually, one of the expression is we call a left-hand side expression, and the other expression we call a right-hand side expression. And these two expressions for same input would produce the same output. Okay, so here is an and this would be called and this holds for all inputs. This holds for all possible inputs. Then it would be called a axiom or a law. It should be called a law. So here is a common law in set algebra. You know the De Morgan's law, that is the complement of A union B is A complement intersection B complement. So this is a law. The left hand side and the right hand side expression, for whatever value of A and B you take, they would produce the same set. They would produce the same set. So this is a law. And it's easy to verify this law. If you, this is a simple Venn diagram kind of thing. So if you take any A, any B, and A union B is this pink area, and similarly you take the complement of A, which is the area outside A, and complement of B, which is the area outside B, and if you take their intersection, you see it again becomes this pink area. So you have kind of, well, this is not a proof really, but you have kind of convinced that this is true. De Morgan's law holds. You have the dual De Morgan's law, which says we'll come back about this. Every algebra has some dualities in terms of their operators. We'll talk about these dualities. You see the difference between the first law and the second law is only that we have interchanged the union with the intersections. We have just interchanged the union with the intersections. Okay, so it's the dual law of the first law. Okay, what the dual law says, that the complement of A intersection B is complement of A union complement of B. So this is another law. This also you can easily verify using the Venn diagram. Okay, there is one more. So there are many other such laws of set algebra. There are other sub-laws of set algebra, and why these laws are useful? Again, you can see that this left hand, what this law says is that left hand side is equivalent to is equal to the right hand side. That means for same input to the left hand side as well as the right hand side, we would get the same output for all possible inputs. So since they are equivalent, if I have an expression involving the left hand side, I can substitute the right hand side instead. So you have an expression where a part of the expression involves the left hand side of a law. You can as if substitute it by the right hand side without disturbing the expression. The expression is the same, remains the same if you substitute the left hand side by the right hand side. That means you have transformed an original expression into another expression without disturbing the validity of the expression. That means the expression logically is the same, but it is expressed in a different way. The different way I have obtained by applying this law for transforming one into the other. And again, as I said before, we are interested in some transformation in the first place because we want to do a series of transformations so that we end up with the final expression, which is a simpler or a smaller expression in terms of number of gates you require to implement it, in terms of the say the power you burn to run that circuit, or the timing delay of the circuit, whatever it is. In some terms, it is a better expression to implement. Okay, so that's why these laws in the algebra are important to us. We'll study them. Okay, let me define another important thing in the set theory, which will be useful to us later. It's the definition of power set of a set A, denoted by this script PA. Power set of a set A. So the power set of a set A is another set whose elements are not elements of A, but subsets of A. So the power set of a set A is a set whose elements are all possible subsets of A. This also I think all of you know, whose elements are all possible subsets of A. So if your set is say only two element set A comma B, A and B, two element set, then all possible subsets are null, only A, only B and AB, full A itself. So this 4 element set, note that the elements of the power set of A are not this A or B, they are subsets of the set AB. So they are sets themselves. So null is a null set, empty set, A is a singleton set, B is a singleton set, AB is a 2 element set. So these are the elements of subset. So naturally, you can easily verify that if a set A has a cardinality n, the power set will have a cardinality 2 to the power n, because there are 2 to the power n possible subsets of A if A is of cardinality n. Okay. There is another definition would like to have. Let x1 to xa be a collection of subsets of A. So you take a collection of subsets of A. So basically x1 to xa are nothing but elements of the power set of A. These are nothing but the elements of the power set. You take any element, this would be well, let me see if I can write. Why is this pen not working? Anyway, forget it. Okay, so let's pick up elements from the power set x1 to xa. This collection of elements x1 to xa, note that I do not talk about single elements x1 to xa. I talk about some collection of x1 to xa, would be call it a partition of A if they are exhaustive and exclusive. Exhaustive means if they are exhaustive. So if you take the union of x1, x2, x3, xk, you get back A. Okay. So if you put together x1 to xa, you get your full set A. That means this is called the exhaustive property. And if you take any two xi xa from I equal to 1 to k, j equal to 1 to k, if you take any two xi xa, they have an empty intersection. There is no overlap between any of xi xa. They have an empty intersection. If I not equal to j, of course. This is the exclusivity property. Okay. So if a collection of subsets x1 to xa follow the exhaustive and the exclusivity property, then that collection is called a partition of A. It's called a partition of A. I think this is also clear to you, but let me see if I need to draw a diagram. Just to explain. Maybe you remember all this, but I'm not sure what you remember. Okay, so let's check this is the set A. And this is I'm drawing a number of subsets of A, and I'm calling them x1, x2, x3, x4, x5, and x6. You see, if you take x1 union x2 union x3 union x4 union x5 union x6, you get back A. And similarly, if you pick up any two, let's say x3, x2, you get a null. They do not overlap. So this collection x1 to x6 is a partition of A. Is a partition of A. Okay, simple. I mean, I am sure all of you know this. Okay, so these are two important definitions, the power set and the partition, which you keep in mind. Here is an example. See, this is also an important example. So there is one partition which any set has. So if you any universal set has. So if you take the universal set U, which is this rectangle, and given any two sets A and B, then the subsets of U, the following subsets of U, A intersection B bar, that is this area, B intersection A bar, which is this area, A intersection B, which is this common area, and A union B bar, which is this pink area. Four sets constitute a partition of U. So given any two sets A and B, they naturally produce a partition on the universal set U, and the partition is just this. They always produce a partition. Okay, so I am writing down here some of the laws or axioms or rules of the set algebra. And again, I repeat, rules means I have two expressions, and I say that these two expressions are one and the are equivalent for whatever value of the input operands. For whatever value of the input operand, always left hand side and the right hand side two algebraic expressions are always the same. They may have different operators, may have different operands, but they evaluate to the same thing for all inputs. That's important for all inputs. Okay, so let's write down some. Some such laws of set algebra. Again, I repeat, the purpose of this law is that if you have a expression, you can sort of reduce the expression by applying this law. That means substituting the left hand side by the right hand side. Okay, idempotence. Idempotence, what it says is that if you take a set A and union it with itself as many times as you want. I have written here 2 times, but it actually holds if you apply it as many times as you want. Say A union, A union, A union, A union, A, you get A. Okay. So it's kind of with itself, if you apply union, whatever number of times you want, you still get back A. Okay. So in some sense, this applying union with itself is kind of meaning useless. It gives you back the same thing. And the similar thing holds from A intersection A also. As many times you apply the intersection operator on with itself, you get back the same thing. Okay, so this is idempotence. Then you have associativity. Okay, by the way, one more thing I forgot to mention, that I said that expressions in an algebra are some operands, in this case some sets, and some operators, in this case only 3 operators, union, intersection, and complement. And these operands combined by this operator. There is one thing you can use in expressing and in writing down an expression are parentheses, which basically tells you the precedence or the order in which you should apply the operators. It tells you about the precedence, the orders in which you should apply the operator. For example, if I put a parenthesis here, this means that first you should take the union between A and B, and whatever is the result, with that you should take union of C. So you can apply parenthesis. It has the usual meaning in normal algebra that you studied also. Okay, so what associativity means is that you can change the position of your parenthesis. You can move the position of your parenthesis, and still the expression should remain the same. Still the expression should remain the same. So, for example, if you first do what that again means is that you can change the sequence, or you can change the order in which you perform the operations, and you get it doesn't matter in what order you perform the operations, you get the same results. So, for example, if you first take union of B and then take union of C, the result that you would get would be one and the same of what you get by first take union of B and C and then taking the results union with A. The overall result will be same for both, whatever value of A and B and C. Okay, so this is associativity. What associativity basically means is that you can change the order of evaluating the expressions if the expressions involved are of this form. If the expressions are of this form. Okay, the associativity, there is one more associativity that holds. If you have an expression A intersection B union C with a parenthesis here, that means first you evaluate A intersection B and the result you union with C, whatever you get is one and the same as first you take the union of B and C, so and then you take the intersection with A. So you see, I have just moved the parentheses. I've just moved the parentheses. I've changed the order of computation. But that doesn't affect the result. Okay. Any questions so far? Okay. I hope all of you are listening. Anyway, so commutativity. Commutativity means that you can change the position of the operands. So A union B is same as B union A. You can change the order of the operands. You can change the position of the operands. Similarly, A intersection B is B intersection A. And then you have distributivity. You usually say that union distributes intersection. That means if you have A union within bracket B intersection C, it's just the usual whatever you have done in normal arithmetic, integer arithmetic or floating point arithmetic, whatever you have done, similar thing happens in set algebra also. Whatever done you in normal algebra, in high school algebra, over numbers, you have the same thing in here also, for sets also. So union distributes intersection. A union B intersection C is A union B intersection A union C. Similarly, but this rule you see, okay, this also distributes. So A intersection B union C is A intersection B union A intersection C. Okay, this also distributes. Then you have an identity. That means if you take the union of A with the null set, you get A. If you take union of A with the universal set, you get the universal set. Similarly, if you get the intersection of A with null set, you get the null set. If you take the union of A with the universal set, sorry, this would be intersection. This would be intersection. Intersection of A with the universal set, you get back A. So you see again, I think you have noticed one thing, that left hand, this first column, the rules I have written down in the first column and the rules I have written down in the second column, they are just dual of each other. If you interchange the union with intersection, you get one rule from the other rule. They are dual of each other. Okay, involution. So this is a very important rule. This are relaxed in some exotic kind of sets. So the complement of a set A is the set itself. Complement of set A is the set itself. And then there are some rules involving complements. The complement of the universal set is the null set. The union of the set, any set A with its complement is the universal set. The complement of the null set is the universal set. Intersection of any set A with its complement is the null set. That's the definition of the complement set, is the null set. And finally, you have the De Morgan's law, which is, I have stated before, complement of A union B is A complement intersection B complement. Complement of A intersection B is A complement union B complement. Okay, so these are all the rules or axioms or laws you have in set algebra. And these are always true, in the sense that whatever may be the value of A, B, these are always true. It doesn't depend on a particular A or B. Okay, now let us quickly recapitulate what a relation is. First, let me define what is a tuple. A tuple is nothing but an ordered pair of set elements. So this is a two tuple A in A, B, represented by the left angle and the right angle, enclosed in the left angle and the right angle. This is the next one is a three tuple, where 4B alpha are elements of some set. Cartesian product of two sets A and B is another set comprising whose elements are all such tuples. All such tuples means all possible tuples you can ever construct by using elements from A and B. So you pick up any element from A, pick up element A from A, pick up any element B from B. Their ordered pair AB is a valid tuple and is an element of the Cartesian product A cross B. And if you allow this if you allow all possible such tuples, the set you get is the entire Cartesian product. So if the set A has m elements and the set B has n elements, the kernelity of the Cartesian product is m times n. So here are some examples. So ABC is one set A, alpha beta is another set B. You include in the Cartesian product all possible ordered pairs comprising elements of A and elements of B. Okay, now we define a binary relation R on the set A and B as any subset of the Cartesian product. Okay, you pick up any subset of the Cartesian product, we call it a relation on the set and A and B. For example, this is a Cartesian product of this ABC and alpha beta set. You take the first three elements, you take the subset of A cross B comprising of the first three elements, that would define a relation. That would define a relation. And so all these ordered pairs would be called, since this relation R, this would be script R. Relation R is a subset of A cross B. We would say that one particular ordered pair or element of the Cartesian product belongs to the relation or do not belong to. So for example, if I have a relation comprising of A alpha, B alpha and C alpha, this is my relation, then these three tuples would belong to this relation and the other three tuples will not belong to this relation, because relation is a set. We can sometimes, which basically means is that you can define the relation as an indicator function or a characteristics function over the Cartesian product set. That means I have a kind of function which gives a value 1. So this function, what this function does, if you take any element of the Cartesian product, any ordered pair belonging to the Cartesian product, this function would produce a value 1 or a 0. It would produce a value 1 if that particular tuple belongs to the relation R, the subset R, and 0 otherwise. So it's kind of an indicator function or a characteristics function over the Cartesian product set. It basically denotes that you take a Cartesian product set, you pick up an element, it satisfies the relation or doesn't satisfy the relation, it just says that. You can take examples. For example, let's say ABC is the set of all okay, let ABC is the set of all countries, say 3 countries, say India, Bangladesh and Pakistan, or 3 states, let's say Punjab, Haryana and say Tamil Nadu. So these are 3 states, and alpha beta are some cities, let's say Chandigarh and say Madras, Chandigarh and Chennai. And let's say I can, so all ordered pairs are, let's say Punjab, Chennai, Punjab, Chandigarh, Haryana, Chandigarh, and so on. Okay, Punjab, Haryana, Chennai, and so on. So all these ordered pairs are, say, and we'll say a relation is if the one city is the capital of that state. Okay, so the pairs, say Punjab, Chandigarh or Haryana, Chandigarh belongs to that relation. Tamil Nadu, Chennai belongs to that relation. Other tuples, say Punjab, Chennai, do not belong to that relation. Okay, so this is, so a relation is nothing but a subset of tuples. Which subset? Punjab, Chandigarh, Haryana, Chandigarh, and Tamil Nadu, Chennai. These three element subset of the product set forms the capital relation. Okay, and what would be the indicator function? The indicator function of the characteristic function would be 1 for these three tuples and 0 for the other tuples. All right, so there can be, for example, other things like if A and B are the same set. For example, if A is the set of all positive integers and B is also the set of all positive integers, that is Z, we can talk about a relation called divisibility relation. That means one element A and another element B are related to each other if A divides B without remainder. A perfectly divides B. So 2 divides 4. It's a member of the dividing relation. So you can easily give examples of such relations. Okay. Just to quickly recapitulate for people who have not done the discrete structure course. A Cartesian product of two sets is all possible tuples that you can construct using pair of elements, one from each set. A binary relation on the sets A and B is some subset, maybe it includes everything in, is some subset of the Cartesian product A and B. For every binary relation, you have a characteristic function which marks the elements of the cross of the A cross B, which satisfies the relation or doesn't satisfy the relation. That means belongs to R or doesn't belongs to R. Now let us talk about some properties of the relations that we talk about. Okay, so one relation is called reflexive if an element X of A is always related to itself. Okay, is always related to itself. So if you pick up any X from A, the relation X R X always holds. Okay, so any element of set A is always related to itself. For example, the divisibility relation, if we talk about, any integer divides itself. So reflexibility holds. If this thing holds for all X, then we say that particular relation is reflexive. Okay, a relation is called symmetric if for any X and Y in A, if X is related to Y, it implies Y is also related to X. If X is related to Y, Y is also related to X. Okay, and this should hold not for any particular X and Y, but all X and Y in A. This is an important point. This should hold for all X and Y in A. All X and Y in A. So if you pick up any two X and Y, if I find that X is related to Y, if they're not related, I cannot say anything. If X is indeed related to Y, then definitely we can say Y is also related to X. If this is true, then I call the relation to be symmetric. The divisibility is not a symmetric relation. If A divides B, doesn't mean that B divides A. Transitivity. If you have three elements X, Y, and Z in A, note that I am talking about earlier. In general, the relation can be defined over two sets A and B, binary relations. But I am taking a special case where B is same as A. So I am talking about relations which are subset of A cross A. A cross A. Otherwise, this doesn't make sense. I'm talking about relations A cross A. Okay, transitivity. If you take three elements X, Y, and Z, if X is related to Y and Y is related to Z, it implies X is related to Z. Okay, so let's see what this means actually. Let me draw a diagram to explain this. Okay, let's say this is element X, this is my one element Y, and this is my one element Z. What does reflexivity mean? So how I will represent relations? I will represent relations by directed arrow. That means if X is related to, I will draw a directed arrow from X to Y. I'll draw an arrow from X to Y. Okay. Similarly, if X is related to Z, I'll draw an arrow from X to Z. I'll draw a directed arrow. Okay. So if R is reflexive, what it means? For all the elements, let's say there are only three elements. There are only three elements in A. For all the elements, so X is related to X, Y is related to Y, and Z is related to Z. This means I have this kind of self loops. I have this kind of self loops. Okay. Now let us look at symmetry. Which means if X is related to Y, implies Y is related to X. What it means? If I have an arrow from X to Y, it definitely means there is a back arrow like this. And this should hold for all XY. For all XY. Okay. So let's say I have two relations. So let's say X is related to Y, it definitely means this will be there. Let's say Y is also related to Z. It means this back thing will be there. Now let us look at the third condition, which is transitivity. This means if X is related to Y and Y is related to Z, as we have drawn, it implies X is related to Z. So that means if I have this arrow and I have this arrow, I definitely have this arrow. Okay, I definitely have this arrow. And by symmetry, if I have this arrow, if symmetry holds, they may hold independently, but if all three of them holds, then I also have this. Okay, so that means you see, if all these three properties hold for a relation, it's kind of there is a strong connection between X and Y and Z. If X and Y and Z are related by symmetry, transitivity, and reflexivity, then they are kind of intimately, they are all connected to each other. They form a kind of a single unit like this. Okay, so if all these three property holds, I would call R to be an equivalence relation. Equivalence relation. So if X, Y, and Z are related by an equivalence relation, you see there is a kind of strong connection between them. They're completely interconnected to each other. That's when we call this as an equivalence relation. So one of the common example of equivalence relation is this. So if you take A, the set to be all integers, all positive, all integers, let's say. And the equivalence relation R is nothing but if two integers are same. If two integers are same, if x and y are identical, then only we call it as equivalence relation. Of course, it is kind of, it is reflexive. That means an integer is related to itself. It is symmetric. If x is equal to y, y will definitely be equal to x. It is transitive also. If x is equal to y and y is equal to x, x is equal to z, x is equal to z. Okay, so equality is the over the integers or any other thing is the classic example of an equivalence relation. So it means in this diagram is that everything is kind of related to each other. But often in many relations, this may not be true. Where do you close? Hello. Oh, okay. Okay, I am giving that. In fact, there is another example we can talk about. Let's quickly do that. Let's say our set is all lines, straight lines in 2 dimensions. Maybe it holds for, well, in higher dimensions we don't call it a line anymore. But let's say our set consists of all lines in 2 dimensions. This is our set. Let me call it as, say, L. And so let's say L1 is a line, L2 is a line. So I have L1 and L2. We'd say that L1 is related to L2 if L1 is parallel to L2. If L1 is parallel to L2, I say L1 is related to L2 over the set of all possible lines in 2 dimensions. Now you see it's reflexive. It's reflexive like a line is parallel to itself. It's symmetric. That means if L1 is parallel to L2, then definitely L2 is parallel to L1. And L1 is always parallel to itself. L1 is always parallel to itself. And also it is transitive. Because if you have these are not straight line anyway. So I cannot draw a straight line. It's very difficult to draw a straight line. Okay, let's say they are parallel and straight lines. So L1, L2, L3. So if L1 is parallel to L2 and L2 is parallel to L3, then definitely L1 is parallel to L3. Transitive, very simple. So these are very simple things. So I think you can sort of think of this parallel property of parallelism of 2 lines is a relation among all lines. If 2 lines, I'll say, will be related if they are parallel, and they form this equivalence relation. They satisfy all these 3 properties. If a relation satisfies all these 3 properties, we call the relation to be an equivalence relation. We'll see that there is one more thing you can, let me just talk about it. So suppose among all possible lines in 2 dimensions, suppose I group them into things like so I said that you have already talked about partition earlier. That means if you take a set and if you take a collection of subsets which are exhaustive and exclusive, then they form a partition. So if you take the set of all possible lines in the world, and then you group them into, say, groups such that they are parallel to each other. So all lines which are parallel form a group. All lines which are parallel to each other form a group to form such groups. And you will easily see that this is a partition in the sense that these are exclusive. Of course, if two lines are parallel to each other, they would belong to the same partition, they would belong to the same subset. And if they do not belong to the same subset, they intersect, they are not parallel. Of course, I'm talking about Euclidean geometry. And then they are exhaustive, because what I have done is that I have taken all possible lines and I have taken subsets which are so if I take all possible lines and I take subsets which are parallel to each other, of course they will be exhaustive. That means I'll be not left out with a line which is not parallel to, it will be parallel to somebody. So it will always belong to a partition. So it is exhaustive. So this is another example. There are many more examples of equivalence relation. Okay, so there is, I think equivalence relation, those who have studied discrete structure might have studied in great details, but there is, we are not really interested directly in equivalence relations here. We are interested in another type of relation where I would replace the symmetric property by something called an antisymmetric property. A symmetric property by something sort of antisymmetric property. So what is the antisymmetric property? A relation R over A cross A is said to satisfy the antisymmetric property if you take any x and y from A. If you take any x and y from A, if both x and y, if both the tuples x and y and x, so if x is related to y as well as y is related to x, it would mean that x is same as y. Okay, it would mean that x is same as y. That means if x is related to y, then either y will not be related to x or y will be equal to x. Either they will be equal or they will not be related at all. So that means so see, so if we look at a relation, if we see that if it will be antisymmetric, it will be antisymmetric if you see you look at the relation. Relation is a subset of the Cartesian product. Okay, so relation is nothing but a collection of tuples, sum of the tuples of the Cartesian product. If you examine the tuples, if you see that let's say AB as well as BA exist, it means A is equal to B. Okay, both cannot. Both xy and yx cannot exist until and unless both x and y are same. In other words, it means that if we find that x is related to y and we also find that y is related to x, you can say that x is equal to y. One simple example, let's take the set of all integers and say A is the set of all integers, and I will say x is related to y if x is greater than. So equivalence relation, symmetric relation, we talked about x is equal to y. X is equal to y is an equivalence, or that means also symmetric. Let's take x is greater than equal to y. So if x is greater than y as well as y is greater than equal to x, it will definitely imply x is equal to y. If x is greater than y and y is greater than x should be equal to y. Okay, so this greater than equal to is an example of anti-symmetric relation. Just equal to is an example of symmetric relation. So in some cases, note again that this should hold for all x, y in A, not just for a single particular instance of x and y, all x and y in A. Okay, so this antisymmetric property, of course, I mean, if for equivalence relation we need reflexive symmetric transitive, but sometimes if we instead of symmetric you have the antisymmetric relation you may also have, and that's also interesting. There is one more relation we'll later talk about. It's called an asymmetric relation. That means for all x, y, if x is related to y, then definitely y cannot be related to x. Y cannot be. You rule out y is related to x. In the antisymmetric relation, you don't really rule out. You say that it means x is equal to y. In asymmetric, if x is related to y, you completely rule out y is related to x. If x is related to y, if AB is there, BA cannot be there. BA cannot be there. Okay. If AB is there and BA is there, it means A is equal to B. In asymmetry, if AB is there, BA cannot be there. Example, let's say, again, take a set of all integers and you say that A is related to B if A is greater than B, just greater than, not greater than equal to, just greater than B. So that means if A is greater than B, under no circumstances B can be greater than A. Whereas if A is greater than equal to B, still B can be greater than equal to A if A is equal B. But if strictly greater than, if we take, if A is greater than B, B cannot be greater than A. This is an example of an asymmetric relation. Antisymmetric is greater than equal to. One example, of course, I'm just giving examples. Let us talk about, let us look at what it means in terms of the diagram that we had drawn. Okay, again, let's take three elements, x, y, z. Let's take an relation R denoted by an arrow. So if x is related to y, I will draw an arrow from x to y. So in case of equivalence relation, the arrows would look like this. If x is related to y and y is related to z, then x also will be related to transitivity. And by flexibility, all the self loops will be there. And important thing, let me change the color. Anyway, let me draw a dashed line. So the symmetry property says that for equivalence relation, if x is related to y, y should also be related to z. So this is the symmetric property. Okay, this is the case of equivalence relation. Now suppose I replace the symmetric property, other two properties are there. Other two properties are there. That means self loops are there. This is related to this is related to this, so transitivity is there. But this symmetric edge, symmetric arrow is not there. Okay, symmetric arrow is not there, so I have an anti-symmetry. If that arrow is there, it means they are the same element. X and Y are the same element. If this other arrow is there, okay, they are the same element. So again, to this definition. Okay, so let me now write down the definitions that I am looking for. Equivalence relation: a relation R is an equivalence relation if it is reflexive, symmetric, and transitive. A partial order, I am defining a new type of relation. A partial order, a relation R is a partial order if it is reflexive, transitive, just as an equivalence relation, but you replace the symmetric property by the antisymmetric property. Okay, and okay, one property I've talked about is that the equivalence relation has always induces a partition and vice versa. A partition also induces an equivalence relation, but well, that is what a property of the equivalence relation. But let's talk about partial order. A partial order is kind of a relation which satisfies reflexive, transitive, and instead of symmetric, antisymmetric. So if X is related to Y and Y is related to X, implies X and Y are the same. X is equal to Y. Okay. So you know what? So now let's define. This is a partial order. Now let us look at one more property of the relation. Okay. Let me just quickly mention one more thing about this partial order. Okay, so let's take three elements, X, Y, and Z. Okay, so self loop, if it is a partial order, self loops will always be there. Reflexivity will always be there. Let's say X is related to Y and Y is related to Z. So this means by transitivity, X will also be related to Z. By transitivity, X will always be related to Z. Now, note one important thing. See, if it was an equivalence relation, this back arrows would be there. So if X is related to Y, Y would also be related to Z or related to X. So these back arrows would be there. But if it is a partial order, that means it is antisymmetric. That means these back arrows are not there. Okay, if it is symmetric, the back arrows would definitely, for every arrow there would be a back arrow. If it is antisymmetric, the back arrows won't exist. There is only one arrow. The back arrow is not there. This has an important implication. This means I can, if I arrange this X, Y, and Z geometrically, if I place them in a particular order, the arrows are only in one direction. Arrows are only in one direction. There is no back arrow. The arrows can all be aligned in one direction. So what I do is I take a convention that all arrows point up, because arrows are in one particular direction. So I arrange X, Y, and Z in such a way that all arrows point up. All arrows point up. Right? So can I do this here? Can I do this here? Rather, instead of this, I rather say that, okay, all arrows point up. So can I kind of do this here? What arrangement to do this here? So this is X. Let's say this is Y. This is a particular geometric arrangement of X, Y, and Z. So X goes to Y, it goes up. Y goes to Z, it goes up. and x gets to z, it goes up. And these self loops are there. Okay, so if I adopt this convention that all arrows point up, I can actually drop the arrow and replace them by lines. So I can just represent them this way. Okay, because I already have the convention, I can automatically put the direction of the arrows because I know all arrows point up. For this, I have to arrange the x, y, and z geometrically that way. Okay, so this I can do without losing information. And since I know that self loops are anyway there, always self loops are there for all x, y, and z, I can drop the self loops. Yes, they are implied. I can drop the self loops. Okay, not only that, since I know transitivity is there, I can drop the transitive edges also. So I can just write it this way. Okay, so just this diagram is enough for me. This diagram is enough for me. From this, you can see I can easily reconstruct this diagram. What I'll do the reconstruct, I'll put the direction to the arrows upward, and by transitivity, I'll connect x to z, and by reflexivity, I'll put the self loops. Okay, but this is a so from this diagram I can reconstruct, but this I'll prefer this diagram, this last diagram, because it is cleaner. It's easier to look at. It's cleaner. Okay, so this diagram is called a Hasse diagram. It's called a Hasse diagram. It's kind of a graph-like of thing where the nodes are the elements of the set and edges are representing relations. Okay. In partial order, sometimes if there is edges, we say x is compared because you see this x is related to y. This r basically means we will sometimes say x is comparable to y. X is similarly y is comparable to z. And this diagram, so you represent this partial order structure on certain sets by this kind of Hasse diagrams. They basically represent these loops. Sorry, this graphical structure. Any questions? Any questions so far? Hope I'm audible and visible. Anyway, so let us look at another property of this kind of relations. So I'll call a relation to be connected if you take any two elements of A, x and y, either x and y are comparable or y and x are x and y are related or y and x are related. So either x is related to y or y is related to x. Say you take the relation over integers less than equal to. So you take any two integers, either the any two integers x and y, either x is less than equal to y or y is less than equal to x. Either of these will be there. So then we call it so basically it means that if you take any two elements, there will be an edge between them. Okay, either y x will by the Hasse diagram, either x will lie above y or y will be below x, but there will be an edge between them. Okay, if a partial order is connected. Okay, one more thing. Instead of so I am still representing partial order by the script R symbol. Sometimes because it originated from this less than equal to kind of situation. So this partial order is sometimes represented by this symbol, this kind of specialized less than equal to. So this symbol is well, I mean, it's better to write it as a R, but sometimes for convenience we write it as this less than equal to symbol on the as a partial order. So instead of R, I will write X, this symbol, and then R, then Y. Okay, X, this symbol, Y. Okay, a connected partial order is called a total order. A connected partial order is called a total order. Okay, a connected partial order is called a total order. Let me talk about some other properties that will hold. For example, there is something called a irreflexive relation. That means that in the diagram that you saw, the self loops are not there. X is never related to itself. X is never related to itself. Okay. Typical example, say over the integers, if we take the strictly greater than relation, so an integer is never related, is not greater than itself. Okay, so it's an example of irreflexive relation. So irreflexive relation is one, so that for all x, x is not related to itself. Asymmetric, we talked about earlier. If x is related to y, y cannot be related to x. If x is greater than y, y cannot be greater than x. It's an asymmetric relation. Okay, by the way, one more thing, this total order, let me see how the Hasse diagrams look like in the total order. Okay, so let's have 4 elements: x, y, z, let's say u. Okay, so this is an drawing a Hasse diagram. So let's say this is a Hasse diagram. Okay, now let's say in a total order, see there will be so either if you pick up any x and y, either x will be related to y or y will be related to x. So is this a total order? But let's say look at this kind of thing. Note one thing, that I have not done the transitive relation. So if this is there and this is there, of course this is there. Similarly, okay, this is the only transitive relation we have here. This is a transitive relation. So now if I complete it in terms of the transitive relation, is it a total order? Anybody answer this? Is it a total order? Total order means if you pick up any 2 elements in this diagram, if you pick up any 2 nodes, there will be a connection between them. There will be a relation between them. In the Hasse diagram, we don't draw the transitivity, but you have to infer them. So is it a total order?
No, Z is not related with Y.
Repeat again, your voice
Z
dropped.
is not related with Y.
Exactly. Z is not related to Y. But let's take this situation. Yeah. Is this a total order? Is this a total order? Because you know, by transitivity, I can draw this. And I can draw this.
Yes, sir.
Okay. So this is a total order. So if we think a little bit, you will see the Hasse diagram for the total orders will always look like a chain. Will always look like a chain. Okay. So moment you see a Hasse diagram which is like a chain, if you draw the transitive edges, you can see that it will be a total order. All right, so this is some trick kind of. If you just look at the Hasse diagram, you can immediately say it is a total order if it looks like a chain. Okay, so we have talked about equivalence relations, we have talked about partial order, we have talked about connected partial orders, which are total orders. Now let us talk about another type of relation. Okay, so let's look at some of the property. So let's talk about a relation which has these two properties. It is irreflexive. That means the self loops are not there. X is not related to itself. It is asymmetric. That means if X is related to Y, Y cannot be related to X. You rule out YX. If XY is there in the relation, you rule out YX. It's asymmetric. It's in antisymmetric. If X is related to Y and Y is related to X, in only one case it is possible when Y is equal to X. Here, in no case it is possible. So 1 is greater than equal to, this is strictly greater than. Okay, N relation would be called a strict order. A strict order if that relation is irreflexive and transitive. You can easily show that if it is irreflexive and transitive, it will also be asymmetric. It follows. It will also be asymmetric. So a irreflexive and a transitive relation forms what is called a strict order. Now, you can convert a partial order into a strict order and vice versa, a strict order into a partial order by slightly changing the definition of the relation. By slightly changing the definition of the relation. For example, this is a partial order. See this kind of special type of less than equal to. Suppose this is a partial order and A. This is a partial order and A. What I do, I define a, so this is a relation. That means if X is less than equal to Y, this I'll say that it belongs to the partial order. I define another relation. Instead of this special type of less than equal to, I call it less than. I call it less than. And this less than I will define using this less than equal to by slightly modifying this less than equal to. I will say X is less than Y is defined this way. X is less than Y is defined this way. If X is less than Y, if X is less than equal to Y and X is not equal to Y. So I will say X is less than, very intuitive. If X is less than Y, if X is less than equal to Y and X is not equal to Y. Okay. So if you define, if this less than equal to is a partial order and this less than is defined using this less than out of this less than equal to, then this less than forms a strict order on A. This forms a strict order on A. Okay. So you can convert a partial order into strict order by changing the definition of the less than equal to relation by just ending the not equal to condition. By just ending the not equal to condition with the partial order condition, which is X less than equal to Y. Similarly, if just less than is a strict order, then I can define a less than equal to new relation as follows. I'll say X is related to less than equal to Y if X is less than Y or X is equal to Y. So here also I just slightly extend this definition by ORing it with the equal to definition, equal to condition. Then this new relation X is equal to Y is a partial order. Okay. This you can take any example, you can work this out. You can take any example. Say the divisibility. Divisibility is a partial order. And if you don't consider a number dividing itself, then it becomes a strict order. Okay, so here is an example. Okay, I think here also you can easily convert one to the other. Let's take this example. So these are some Hasse diagrams. Let me explain what these Hasse diagrams are. And using these examples, I'll introduce two more concepts. Let's take a set 0, 1, 2. Let's take a 3-element set 0, 1, 2. Let's consider the elements of the power set of this set. So power set of a set, as I have said before, is all subsets. So null is an element of the power set. All these singletons are element of the power set. All these 2 elements are elements of the power set. So my A, or the set over which I define the partial order, is the elements of the power set, or all possible subsets of the 0, 1, 2 set. Now let us define the relation as follows. One subset is related to other subset if it is contained in that subset. So 0, 2 is contained in 0, 1, 2. So there is an edge from 0, 2 to 0. Note that I am not putting the direction because all edges go up. All directions go up. So 0, 2 is contained in 0, 1, 2. So every edge that you see here is a containment set, containment relation. Now you can easily see the containment set. So null set is contained in every singleton set. Every singleton, these 2 singleton set 0 and 1 are contained in this 2 element set 0, 1. Singleton set 0 and 2 are contained in this set 0, 2. Singleton set 1, 2 is contained in this set 1, 2. Now each of these 0, 1 is contained in 0, 1, 2. 0, 2 is contained in 0, 1, 2. 1, 2 is contained in 0, 1, 2. So this is my partial order. Note that transitivity still holds. For example, 1 is contained in 0, 1. 0, 1 is contained in 0, 1, 2. Similarly, 1 is contained in 1, 2. 1, 2 is contained in 0, 1, 2. So by transitivity, 1 is also contained in 0, 1, 2. Okay, and note that it is an antisymmetric relation. That means if 1 is contained in 0, 1, and as well 0, 1 is contained in 1, it would mean that they would be the same set. If they are not the same set, the back arrow will not be there. Okay, so this is a containment partial order over the power set. This is a integer divisibility. This is a divisibility thing. So you take 36 and I write down all the factors of 36. So 1, 2, 3, 6, 4, 9, 12, 18. These are all the factors of 36. And there is an edge if the lower number divides the upper number. So 1 divides 3, 1 divides 2, 2 divides 6, 2 divides 4, 3 divides 6, 3 divides 9, 6 divides 18, 9 divides 18, 6 divides 12, 4 divides 12, 12 divides 36, 18 divides 36. So this is the partial order set. This is the partial order Hasse diagram. Again, look here, the transitivity is there. 2 divides 36, 3 divides 36, and so on. Okay, so so you can draw these kind of diagrams. Now we define one more thing. So if we have a partial order relation, let's say this, I call it as less than equal to, and I have a set A over which this partial order relation is defined. This pair, the set A and the relation defined on it, partial order relation defined on it, together is called a poset. Together is called a poset. Okay, so you can think of this entire diagram as a poset. It consists of the set A, which is all these nodes taken together, and the relations between them, which is all the edges which connects up the nodes. So this entire picture is that of a poset. Okay, so you can represent posets by this kind of Hasse diagrams. Okay, so now if we take these posets and equivalently these Hasse diagrams, there are two special elements. There are two elements of this poset. Two elements of the A on which are the elements of the poset. What are the special elements? The elements which lie as the bottom, we'll call it as the minimal element, and the element which lies at the top, we'll call it the maximal element, which we'll call it the maximal element. So how do you define this? In fact, this need not, I mean, here I have shown in blue them for the entire poset, but the minimal and the maximal element can be defined for any subset of A also. So if you take any part of these diagrams, they also have a maximal and minimal element. For example, if we look at this part, see this null 1, 2 and 1, 2, if we look at only this small part, the minimal element is this null, the maximal element is 1, 2. Okay, so how do you define? Let's say the maximal element I call capital M and the minimal element I call small m. So they will M or small m will be called a maximal or minimal element of a subset S. I'm defining it as a subset. Of course, you can define it for the full poset also. It's the maximal or minimal for a subset, so that there is no other element in the subset. There does not exist any x in the subset, so that the maximal element is less than the x. So there is no element above this, no element which is greater than this. So this let me first talk about a strict order, then I'll talk about a partial order. Let's say this is a strict order. This is a strict order. So in such a strict order, there is a maximum element, so that there is no other element x which is greater than the maximal element. Similarly, there is no other element x belonging to S, of course inside X, belonging to X, so that it is strictly less than small m, the minimal element. If we replace this strict relation by a partial order, that is the less than equal to relation, instead of the maximal element, you get the maximum and correspondingly the minimum element. So if a capital M is a maximum element of a subset S, similarly small m is a minimum element of the subset S. If for all x, you take any x, it is in the partial order less than equal to capital M and similarly greater than equal to small m. Okay, note this difference between the maximal and maximum. Okay, maximal is you consider a strict order and there is nobody which is strictly greater than the maximum and similarly less than the minimum. Whereas maximum is defined in a slightly different way. So all elements of that subset are related by this partial order that let me call it as less than equal to capital M and similarly greater than equal to small m. So note this. So this is kind of maximal is kind of defined from outside. There is nobody above this. Whereas the maximum is defined from inside. That means everybody inside is below this. Okay. But okay, I am just telling all these words to geometrically you get the intuition, but these are strict definitions. You have to, they need not be geometric things like this. They are less than greater, they may have other meaning. They have many abstract type of meaning. So you have to strictly follow these definitions. When these definitions are well defined, you can easily check them. Okay, so these are other examples. These are other examples. These are divisors of 60. I think let us stop here today. So let me quickly recapitulate. We have talked about relations. We have talked about relations satisfying certain property like reflexivity, symmetry, transitivity. We call them an equivalence relation. Then relations satisfying reflexivity, transitivity, and antisymmetry. We talk them as partial order relations, and we talked about total orders, which are connected partial orders. We talked about relations which are irreflexive and transitive, meaning they are asymmetric, and we call them as strict order relations. And if we have, you can represent partial order by this kind of Hasse diagrams, and you can define minimal and maximal element or minimum and maximum element for this kind of strict order and partial orders. Note that there can be partial orders embedded inside total order. So if you have a total order is like a chain, and then you can have partial orders if we take subsets. So you take baby chains, smaller chains inside the total order, you take baby chains inside them, and then they can form a partial order. Okay, they can form a partial order. Disconnected baby chains you can take. And so partial orders can be embedded. In fact, this is very important. In the Hasse diagram, if you look at chains and if you look at part of chains, and you can easily find partial order and total orders on them. So with this, I think, of course, one thing I didn't take too many examples, but I would request all of you to take in the Kohavi book or anywhere, in the end of the Kohavi book, lot of exercises are there. You should work out some examples. Unless you work out examples, you will forget these concepts. So when I just speak about the concepts, it's easy to appreciate them. It's easy to accept them. They are simple, they are intuitive, but you have a tendency to forget them because they are definitions. They are little bit complicated definitions. So if you practice a lot of example, it will help you to sort of never forget them ever. Okay, so next class we'll talk about some special partial orders. And once you study them, we'll see how they can be used to represent logic circuits and Boolean circuits. Okay, so with this I end. If you have any question, you can ask me. Let me stop the recording.